In this video, we'll generate the EXPONDIST dataset, trend line and trend line equation of EXPONDIST saturation growth curve over the values of lambda from 1, 2, 3, and 4, and the values of x from 0 to 1.2. So we begin with the lambda, data validation, list of items, 1 to 4. So these are our values of lambda, 0, 1, 2, 3, and 4. And we use the array formula to generate the dataset of the EXPONDIST. EXPONDIST of the x values, comma, that's lambda, comma, 1, because it's a cumulative distribution function or saturation growth. So, and we'll chart this using trend line, using scatter chart. Let's chart, we'll use the scatter chart. Scatter chart. And we generate the trend line series, and the trend line will be polynomial to the 6th degree because we all have 6 data sets. And we show the equation as label. And we keep the line thickness 1 thin, but our point size will be maximum 14. So this is the trend line, and we'll relocate this at the bottom. So this is, go back to the legend, relocate it at the bottom for easy comparison with our polynomial regression coefficients. So here's our EXPONDIST, and here's the trend line polynomial. Next, we continue with the equivalent in the exponent form. So we begin with array formula, exponent of the x values. Now there should be an equation. So we modify this, edit chart, show the series trend line. The point size this time will be maybe for May 10. Well, the EXPONDIST is 14. So we'll just reduce it to 10. While the EXPONDIST, make it the largest, and we'll show the polynomial trend line to the 6th degree for the exponent. Exponent has no trend line, so we add a trend line. But the trend line has to be polynomial at the same degree, 6. And we also show the equation as label. There's the equation. Close. So we have the trend lines, and the trend line equation, the polynomials. Now we modify the exponential function. So there's a lambda in it. So times lambda. And there's a negative sign. Enter. But this is decay. So we need to make this saturation. So we factor in 1 minus. So 1 minus. Now they are on the same trend line, and the equations are the same. And we'll modify this trend line of the exponential form. Keep it at 1 as well. So they're on the same trend line. Next, we generate the Taylor Maclaurin series sum expansion, which is equal to the summation of a times x to the power n plus 1. And the value of a, the coefficient, is this, which is negative 1 to the power n times lambda to the power n plus 1 all over factorial n plus 1. And the value for n is from 0 to infinity. We cannot go to infinity, but we'll try to get the maximum, the highest, which is still a good approximation, 12. And we calculate the Taylor-Maclaurin series sum. So array formula, series sum of the x values raised to the power n plus 1. So it starts from 1, comma, and in the interval is also 1 because our n value is 0, 1, 2, 3, 4, 5, up to 12. So it's the interval is 1. And the coefficient will be along the n values. So here we have yellow. We change that to green. So edit chart and the series. This time we'll change this to green. Change it to green. And also we add a trend line. Polynomial. Same degree, 6. And we show the equation as label. There's the equation. But this time the thickness will be maximum. So we have a maximum thickness and the point size will be none. So because this is our reference for this is only an approximation. So okay, close it. Now we continue with the coefficient, which is equal to array formula starting with numerator, which is negative 1 to the power n, times the second part of the numerator is lambda to the power raised to the power n plus 1. So n plus 1. So that's the numerator. Let's enter for now. Then we factor in the denominator. All over factorial n plus 1. N plus 1. They're all in the same trend line. And we have this almost the same regression coefficients. Actually, they're the same. There's a slight error here. And we'll calculate these regression coefficients, polynomial regression coefficients, using LINEST. To do that, we complete the 1, comma x matrix. We start from 0. So that is from 0 to 1. So this will be array formula of the x values raised to the power 0 to 1. 0 to 6. I'm sorry, 0 to 6. Now we can calculate LINEST. So begin with the EXPONDIST. So LINEST data y and data x. For the exponential term, which is LINEST data y and data x. And the approximation, which is the Taylor-Maclaurin series expansion. So LINEST data y and data x. Now let's compare the regression coefficients with the trend line equation, starting from lambda equals 1. At lambda equals 1, they're the same, there's no error, they're all the same, and their datasets are also the same, except for this error. Now lambda equals 2. Now in the dataset we have a slight error starting here. There's an error 881 but 882, and the error gets bigger. But they are the same. They're still on the same trend line. Their trend line equations are also the same. And the regression coefficients, they're the same up to here, but there's an error here, and the error increases. But this is very negligible at x to the 6 higher degree. At n equals 3, or lambda equals 3. So they're the same here. There's a slight error here. The errors are slight. They're still on the same trend line. The trend line equations are still the same, except for a slight error here and a slight error here, 1.02, 1.04. The regression coefficients, they're the same, except for a slight error, some slight errors here, but these are negligible. At lambda equals 4, it's now saturating to 1, and the trend line equations, the regression coefficients are the same up to here, but the error begins up to this portion. The trend line equations, they're the same up to this portion at the third degree. And the data sets, there's the same. The error begins as it goes higher. So this completes the use of array formula, LINEST polynomial regression, series sum in the Taylor-Maclaurin series expansion of EXPONDIST